Hello, everyone. For this video, I'm covering Chapter 6, Firms and their production decisions. Specifically, I'm going to walk through how firms turn inputs into output in the short run, why adding more workers doesn't always help, and what happens when a firm scales its whole operation. First, the four basic inputs every firm uses. Then, short run production, total, marginal, and average production of labor, plus the law of diminishing marginal returns. After that, we'll go long run and talk about SO quants and returns to scale. And along the way, I'll connect it to real examples, including one close to home that you've probably seen on the news. So every firm, whether it's General Electric or a kid's lemonade stand, combines inputs to make a good or a service. Economists group those inputs into four categories, which are labor, which is the human element, both physical and intellectual work, capital, the machines, tools, and buildings, land, the natural resources some goods need, like farmland or forests, and materials, the raw or intermediate goods that get used up, like lemons or steel. Not every firm uses all four. A lemonade stand doesn't need land, for example, but these four categories cover just about everything. Now, economists describe how firms combine those inputs with something called a production function. It is written as Q equals F of L and K. Output is a function of labor and capital. It tells you the maximum output you can get from a specific combination of inputs. Take the lemonade stand. 1 cup of lemonade takes 1 lemon, 2 cups of water, a teaspoon of sugar, and 10 minutes of labor. That whole recipe, that's a production function in its simplest form. Before we go any further, we need to separate the short run from the long run. And this isn't about a calendar, it's about which inputs the firm can actually change. In the short run, at least one input is fixed, which is usually capital, so the firm can only adjust labor. Think of a tablet factory. It can add a night shift, but it can't build a whole new assembly line overnight. In the long run, though every input is variable, given enough time, the same factory could build a second assembly line and completely change its scale of production. So let's stick with the tablet factory for the short run. It's got one fixed assembly line, and we're adding workers one at a time. Look at what happens to output. It jumps from 6 to 20 to 44 as we add the first few workers. Because more workers means more specialization, but then it starts slowing down. 60, 70, 78, and by the time we hit 9 workers, output actually drops from 88 to 86. Too many people, not enough assembly line to go around. That pattern in the table gives us two really important ideas. Marginal product of labor, or MPL, is just the extra output from adding one more worker. Mathematically, change in output over change in labor. Average product of labor, APL, is just total output divided by the number of workers, output per worker on average. Here's the key relationship though. When MPL is above APL, the average is still climbing. Once MPL drops below the APL, the average starts falling as well. They cross exactly at APL's peak. You can see that relationship really clearly on this graph. MPL, which is the gold line, shoots up really fast, peaks around the third worker, and then declines eventually going negative by the ninth worker. APL, which is the navy line, rises more gradually, peaks a little later, and then starts to decline more slowly. Notice MPL crosses APL right at its peak, just like we said. The law of diminishing marginal returns. This is the law of diminishing marginal returns. As a firm adds more of one input while holding the others, the marginal product of that input eventually starts to fall. A few things worth remembering though. The extra output is still positive at first, just smaller each time. It happens because of that fixed input creating a bottleneck. And this is different from output falling overall. Total output can still be going up, just slower. Okay. Let's use a real world example now. Let's see. If you ever eaten out of Hollywood, Florida, this would be the perfect example for you. Picture one kitchen with a fixed number of stovetops. The first cook gets meals out steadily. Add a second and third cook, and things start to speed up a lot. One preps, one plates, one's on the grill. But keep piling on cooks in that same kitchen, and eventually they're just bumping into each other, and each new hire adds less than the last one did. Hire way too many, and the kitchen actually gets slower. That's exactly why restaurant staffs each shift carefully instead of just hiring as many people as they can. The size of the kitchen limits how much labor can actually help them. Okay, not for the long run. Isoquants. Let's go to the long run, where both labor and capital both can change. We use something called a isoquant, a curve showing every combination of labor and capital that produces the same output. There are three basic types, which are perfect substitutes, where the isoquant is a straight line because inputs trade off at a constant rate, perfect complements, where inputs have to be used in a fixed ratio, like one machine needing exactly one operator, and Cobb-Douglas, the smooth, bowed-in curve that's the most common in the real world, where inputs are imperfect substitutes. Now, here's a related but different question. What happens if a firm scales all of its inputs together? So let's say doubling both labor and their capital. That returns to scale, and there are three different cases. Constant returns to scale, output doubles exactly. Increasing returns to scale, output more than doubles. That's two economies of scale kicking in. And decreasing returns to scale, which outputs less than double, usually because it gets harder to coordinate everything at a bigger size. Here's what it looks like with real numbers. All three firms start at 100 units of output, double their units, or sorry, double their inputs from 10 to 20, and their CRS firm hits exactly 200. The IRS firm jumps to 35, more than double, and the DRS firm only reaches 160, which is less than double, even though the inputs are doubled. For Cobb-Douglas function specifically, there's a shortcut. Just add up the exponents on labor and capital. If they equal 1, it's constant returns. Less than 1, decreasing returns. Greater than 1, increasing returns. And here's a real current example. When tech companies build massive AI data centers, they're scaling up capital, chips, servers, cooling systems, and labor engineers at the same time. If a bigger, well-designed facility produces more than proportionally more computing per dollar, that's increasing returns to scale. And it's a big part of why companies keep racing to build ever larger data centers. But push it too far, and power limits and cooling constraints can flip it into decreasing returns. To wrap up, production functions describe the max output from a given set of inputs. In the short run, at least one input is fixed, and that's where diminishing marginal returns to labor show up. In the long run, everything's variable, and isoquants map out the trade-offs between labor and capital. And returns to scale tells us what happens when a firm scales everything up together, which matters for everything from a local kitchen to a billion-dollar data center. That's chapter 6. Thank you for watching. See you in the next video.